Okay, so in this session, I'm going to cover the conservation of mass in differential form. Okay, so far what we learned about conservation laws were all in the integral form, but they also have a form in the differential kind of in differential form, and here I briefly kind of mention how we can convert those integral forms into kind of differential forms. And I will only focus on conservation of mass here and just briefly touch upon that because the conservation of momentum in differential form is kind of out of the scope of this course. Okay, so let's get started. So the mass The conservation of mass states that the mass, or m, of the system remains constant as the system moves through the flow field. Okay. What does this mean? This means that the rate of the change of the mass in the system, or dm sys, or dt, is 0. Okay. So we use Reynolds transport theorem from this. So these are just some reminders from previous chapters. So if we use Reynolds transport theorem, what does this mean is that the dm system over dt equals to, from the Reynolds transport we can say it is equal to, so instead of the total mass I can divide it to all small elements and write this as the integral of these small masses, small elements, over dt, and then instead of the dm I can write it as rho dv, right? So from Reynolds transport theorem, this equals to partial over partial t of the integral over cv of rho dv plus the integral over the control surface of rho v dot n dA. This equals, from this equation, equals to 0. Okay. So this is the integral form of the conservation law, right? So this is the integral form of mass conservation. So now to obtain the differential form, we apply this to an infinitesimal CV, to an infinitesimal control volume, or CV. Okay. So, for example, the partial over partial t of the integral over the whole control volume of rho dv reduces to what? Approximately partial rho over partial t, and then small infinitesimal control volume of delta x, delta y, delta z, right? So imagine this is this infinitesimal control volume that we have. We can calculate the calculating net rate of mass outflow in x direction. Okay. So imagine this is our infinitesimal element, okay, and then this is the coordinate system. This is x direction, z direction, and y direction. So now I can use, in order to calculate these fluxes at these control surfaces, for example, this control surface, if I want to calculate this flux, right, this term, what I want to do is I can use Taylor series, okay? So let me start that. So use Taylor series. I can write rho u, right? So this is the fluxes, right? In the x direction, this is going to be rho u dot n. And then I want to integrate it over this small control surface. So let's calculate that. So rho u at, if this rho u is at the center, now I want to approximate this rho u x plus delta x over half at based on the value in the center. So we have rho u at x plus delta x over half based on the Taylor series. This equals to the rho u at x, right, plus, which is here, right, plus partial rho u, that quantity, over partial x times delta x over 2. And this is what? This is just x minus a if you look at your notes for Taylor series, right? So, and then we have other terms that we can neglect because this delta x is small. So delta x like square is going to be much smaller than delta x and so on. So we can just neglect those terms. And similarly for rho u at x minus delta x half, we have this equals to rho u minus partial rho u del partial x times delta x over half, right? So this x minus a here is actually minus delta x a minus delta x over 2. So that's why we have a negative sign here. And then plus other terms that we neglect, okay? So that is based on the Taylor series. And so now we can calculate the net rate of mass outflow in x direction. So net rate of mass outflow in x direction is going to be what? Is going to be this outflow minus this inflow, right? So we have rho u plus partial rho u over partial x times delta x half times the whole thing times the area, right? Because we have this times dA. So I have to multiply it by the area of this control surface, which is what? Which is delta y times delta z. So times delta y times delta z minus the inflow, which is this rho u minus partial rho u over partial x times delta x half times delta y delta z. And this whole thing equals to what? Equals to partial rho u. These two terms are going to cancel out. Let me see. So I'm only left with partial rho u for partial x times delta, and these two are going to add up. So delta x, delta y, delta z. Okay? And similarly, I can write net rate of mass outflow in y direction. So this is going to be what? This is going to be partial rho. Now instead of u, we have v, the velocity component in the y direction, over partial y times delta x, delta y, delta z. And similarly, the net rate of mass outflow in z direction is going to be what? Is going to be partial rho w over partial z delta x, delta y, delta z. And so total net rate of mass outflow is going to be partial rho u over partial x plus partial rho v over partial y plus partial rho w over partial z times delta x, delta y, delta z. So again, this integral over the control surface of rho v dot n is nothing, dA is nothing other than the total net rate of mass outflow, just for you to remember, refresh your minds. This is in the integral form, and this is going to be in the differential form. Okay, so now let's combine everything together and see what we have. So we had these partial rho over partial t from the first term, right? This is the first term. I can write it as this for in the differential form. So if you combine that with this net mass rate flow, net rate of mass outflow, combine all of them together, what we get is partial rho over partial t delta x, delta y, delta z plus the control surface form is what? Is partial rho u over partial x plus partial rho v over rho y plus d rho w over partial z delta x, delta y, delta z equals to 0. And here the volume of this infinitesimal control volume is going to cancel out. So I am only left with the final form of this equation, which we call it the mass conservation law in differential form, or continuity equation in differential form. Okay, so I'm gonna write that, and then I'm gonna show you some further simplifications, or another operation of the form of that in operator symbols. Okay, so this gives me partial rho partial t plus partial rho u over partial x plus partial rho v over partial v plus partial rho w over partial z equals to 0. Okay, so this is very important equation, and this is actually what we call as the continuity equation in differential form. Okay, so if you remember from your calculus, the divergence operator was defined as follows. A divergence operator was something like this: grad dot of any variable, and what it was giving us was partial over partial x of that variable plus partial over partial y of that variable plus partial over partial z of that variable. Okay, so an alternate form of continuity is as follows: is partial rho over partial t plus divergence of rho v vector equals to 0, right? So this is all, if you calculate it, it's going to be the divergence of this vector. So this is the alternate form of that, and it's a simpler form to remember, right? Because if you know the divergence operator, it's going to be something like this, and then this is the partial over partial t of density. Okay, so for an incompressible flow with constant density rho, what we have is partial rho over partial t is 0. This for the incompressible flow is not changing. So what we are going to have is rho divergence of v. I can bring this rho out because this is constant, right? Equals to 0. And so this means that divergence of velocity should be 0 for an incompressible fluid or flow. So this means partial u over partial x plus partial v over partial y plus partial w over partial z should be 0 for an incompressible fluid or flow. This is an important, very important kind of conclusion for incompressible fluid. So a lot of times you might see when they say we have an incompressible flow, that means just what? That they just mean that the divergence of velocity field is 0. We have an incompressible flow. This is what they mean. Okay? So this is what we call continuity equation. Continuity for incompressible fluid. Okay? So, now let me solve one example of this here. Very simple example. The question asks, determine the form of z component w required to satisfy the continuity equation for an incompressible fluid. Okay, so the question is like this. So we have the u component, which is x squared plus y squared plus z squared, and then we have v component, which is defined as xy plus yz plus z, and then we don't know the w component, and we want to determine it such that it satisfies the continuity equation for an incompressible flow. Okay, so now let me get started with this. What I'm gonna do is, for an incompressible flow, compressible fluid, continuity is partial u over partial x plus partial v over partial y plus partial w or partial z equals to 0. And now let's calculate this. What is partial u over partial x from this equation? It is 2x. What is partial v over partial y from this equation? It is x plus z, right? And what is partial w partial z? We don't know that, so I'm just going to write it down. And so this gives me that partial w over partial z is going to be minus 3x minus z. So w, you need to integrate this, is going to be minus 3xz minus z squared over 2. So let me write everything a little bit, move it to the left. Plus a constant of integration, which is a function of x and y. Okay, so this is constant of integration. Okay, so this is going to be your answer. The form of w is going to be as follows. It's going to be minus 3xz minus z squared plus a function of x and y. This is going to, if you put w as this equation, these three components of velocity are going to satisfy this continuity equation, which is as shown here. Okay, so this was just a brief overview of the differential form of continuity equation, which is like this. and the differential form of mass conservation law, which is shown as here as these two forms. And of course, we can write also the differential form of the momentum equation, which I'm not going to go through that, but just to give you an idea, it's going to be something like partial v over partial t is what we call actually Navier-Stokes equation. So I'm not going to write it down, but you can look at you can look for it. So you will have like all the dm terms, like du over dt term here, and then you will have like 1 over rho grad p and all the forces on the right hand side. So I'm not going to write it down, but just to remind you and give you an idea, if you ever hear this, you have to know what it is. And so the differential form of the momentum equation is called Navier-Stokes equation. Navier-Stokes equation. And this is, we will only teach this in more advanced classes, so I'm not going to go through it here. And it's a completely nonlinear equation, which has not been solved for many decades. So it's an open, so this Navier-Stokes equation, which is just the differential form of the momentum equation, is an open question in mathematics, in one of the millennia's question, one of the 8 open questions in mathematics, is a partial differential equation which has no solution, analytical solution, has not been we have not been able to find any analytical solution for this nonlinear partial differential equation. And so that's why it makes this field very complex and complicated, because we don't have any analytical solution for this, like all other, like most of the mechanics problems that we have, which usually are linear problems. And so in order to solve these a lot of fluid problems, like in complex flows, there we have these complex situations, especially when you have high Reynolds number, and we are going to talk about that. By Reynolds number, we mean like the ratio between the velocity, inertial force, and viscous force. As when your inertia is very high, then the flow becomes turbulent. And so in those turbulent regions, we don't have any analytical solution. So what we are going to do in order to solve this Navier-Stokes equation is using some numerical methods, right? So we solve this momentum equation along with this kind of conservation of mass or continuity equation with some numerical analysis of numerical codes, which we call them as computational fluid dynamics codes, right? So these are just some terms, if you ever hear them. Computational fluid dynamics codes. And there are a lot of these codes available in some commercial codes and some open source codes. Like for commercial codes, we have ANSYS Fluent and some codes like that. And for open source code, there are so many of them, like OpenFOAM is one of the famous ones. And then we have also many other codes. So this equation is very important equation, because even, for example, for weather models, all the weather, like air and water, are all fluid, right? So they have to, what is the equation of momentum for them? How they are kind of transported is through these equations. And so these Navier-Stokes equations are also solved in those codes, and they solve those by numerical methods, right? So there is no kind of analytical solution for these kind of codes, and that's why weather forecasting is very difficult, because one of the reasons is because we don't have we are dealing with very complex formulas, and also the other one is we don't have enough data, and data assimilation is also another problem, and also the resolution is also another problem. So these are some of the reasons why that is not working well. And so just this was just to give you an idea what is this equation, and if you ever hear that in any more advanced fluid mechanics or in later on in your career when you are doing these kind of computations, especially fluid computation or hydraulic fluid structure interaction computations. Okay, so just to have a brief overview of what we learned today, we just derived the conservation of mass in differential form. So what we did, we started with the integral form of the continuity equation or mass conservation, which is shown here, and then we obtained, we assumed kind of infinitesimal control volume, and then we write these, apply this integral form into an infinitesimal kind of control volume. So this is going to be the first term of that, and then the second term would be these flux terms here, or over the control surface, which we wrote it using the Taylor series. We were able to write that and calculate it based on the value in the center of the control volume. Because this is the infinitesimal element, we can use Taylor series here. And we can assume, because delta x is small, we can neglect higher order terms. And what we get is the net rate of mass outflow in x direction, which we found it as this. Similarly for y direction and z direction. And then the total mass net rate of mass outflow is as follows. And if we combine all of them together, we are going to get the continuity equation in the differential form, which is shown here. And then we define the divergence operator as here to kind of write an alternate form of continuity equation. And then for an incompressible flow, the continuity equation in the for an incompressible flow in the differential form reduces to this form, as you see here. And so, and then after that, I just solved an example where we use this formula, and this is an important formula for continuity equation in differential form, to find the kind of one component of the velocity such that it satisfies the continuity equation in differential form. Okay, so this was kind of the brief overview of this chapter, and I'm not going to go through the next part, which is the momentum equation in differential form. And after this, in the next lecture, we are going to start next chapter, which is focusing on Buckingham-Pi theorem. And after that, after we finish that, because that's also a very important fluid mechanics kind of concept, we will start the next the chapter after that, which is on laminar or turbulent flows, and then we go to more engineering side of the course, which will be designing pipe flows and open flow hydraulic channels. Thank you very much, everyone.